Okay, it's a diehard group. I like it. Thanks for coming. We'll let Matt get his beer, and then we'll go ahead and get started. So apparently last week was too much of a fire hose for everybody, and we scared them away. But you guys are the brave. We could choose a few different words. Okay, so I just wanted to start out by saying thank you for coming, but then also we want to modestly re-envision what this looks like. So we're asking for you guys' feedback always, what this could look like. I mean, this is for us and you all that are here. But then also we realized that we've got a wide range of people with a wide range of expertise, right? And so what we want to do is try to make something here for everyone. Because of that, what we were thinking was that we would slightly change the format, where each meetup session that we have now, what we envision doing is having essentially a single activity, and that activity then would have two parts. One part would be to still this sort of zero entry introduction, assuming that you didn't attend the boot camp or attended but don't remember anything from it. We'll slowly go over something together. If this is your one time each month that you commit to trying to learn R, then we need to make sure that everybody has this sort of zero entry slope each time. The second thing that we want to do, though, and the second activity, will be to recognize that there are people at different levels of their training. And so we will have a second part, which is a more advanced exercise or activity. And we will provide the code for both of these. So regardless of your level of expertise, you'll have something to do, something to follow along. So if the advanced sort of section is too much, then we will back off, and we can you'll have the code, and you can sort of scrape from it as much as you will. And then the final thing is we will provide a data set that you can, if you'd like, explore between now and next month. And then next month, we'll go over that data set together. So I provided a data set last month that I said if you want to, you can spend some time with. And I think that will be a good activity, because if you have the time to explore a data set before coming to this, fantastic. If you don't, and you have exactly 1 hour each month to to learn R or to continue this journey, then that's fine too. We will explore it together. So that's the idea. We thought we would have some very task-centric activities before, and these still will be task-centric, but they will also be data set-centric, where we'll be exploring these data sets and then trying to explore them and to learn the functions and learn the packages that allow us to explore them efficiently and effectively. So that's the idea, that's the hope. But before we dive in to the two different parts today, do you guys have any questions or feedback or thoughts?
Just my first ones.
Okay.
I think having something that, like, with style is good. Otherwise, I'm doing all of
Okay. So you like the homework? Great. Yeah, and that was some feedback that we got before. Also, you're not the only one who feels like it'd be nice to have something. So we've got part 1 and part 2 that Ali and Akshay will walk you through, and that's going to be exploring the data set that I gave you guys last month, what we'll call the Prism data set. This is provided by the Broad Institute, and has some really interesting pharmacology data. So we'll explore that a little bit and some visualizations. And then what I'll do at the end to wrap up is I will provide you a data set and the code for it to download, and one simple outline of how you can import the data and then visualize the data and pull some of maybe your favorite gene data out of it. And that will then be homework for you to go in and to change the plot or to pull your favorite gene out, etc. So that's the thinking. Well, the plan here is to keep this under an hour. So without further ado, we will have Ali come on up. Now, while she's coming up, what I want to remind you guys of is that we have you should have a project, an R project folder that has this project in it, this tidybiology meetup project in it. If you don't have that sort of within RStudio, Do they have yellow stickies?
I think only one person.
Okay, so go ahead and anytime you have a problem, go ahead and put a yellow sticky up. But if you don't have the tidybiology meetup project cloned, the repository cloned into your RStudio, go ahead and put a yellow sticky on your computer, and we'll go ahead and help you do that to get you to this point. If you have done this already, what I want you to do then is I want you to, I'll just commit these changes quickly. This is re-knit. You guys don't have to do this. Flip Booker, commit. What I want you to do within RStudio is open up your RStudio project. So it should look something like this. If it doesn't have any files and it just looks like this, that's totally fine. Over on this tab here, you should have something that's called Git, G-I-T. You look in the upper right-hand side. What I want you to do is click on this blue arrow pointing down, and that's a Git Pull command. And what it should do is it should update your project repository with all the files that we put in it for today's meetup. So if you have the project, just double-click and open the project. Go to this Git tab here, click the blue arrow for down to pull down the changes, and you should see they're already up to date for me, so it says Git Pull already up to date, but you should see a bunch of other stuff come up here. If anybody has an error or doesn't get this, go ahead and put the yellow sticky on your computer. And then what you can do is over here, this is what the project folder or directory structure looks like, and you should have a new folder here that's called 2020-_02. This is the code for today, so you can then go to the code folder, and you should see all of these files right here. So, you help?
Yeah, I can.
Okay, no, that's fine. We can get that. All right, so Allie's going to go ahead and start, and if you guys have questions, interrupt.
It said it's going to override.
All right. So, recording staff. Okay, so we have some chunks in here based on
I'm going to wait just a second to get half of the class up to date. Okay, for those of you who do have it, if you could go ahead and we're actually going to go back a little bit, but if you could go ahead and run your first chunk where you load your libraries, and then your second chunk where you're going to pull these data and load the data, okay? Because that might take a second. So we'll go ahead and get it going. Mm-hmm. Actually, is this still loading? Still working? Okay. I figure there's not a whole lot of point going on if there's if half the people. Yeah.
But I couldn't figure out how to do it.
Like
This is
Is that what it
the computer that's installed. That's okay. So this makes it sound like
is?
in
No, I got lines. I actually put verticals. I
It's
wanted
something,
to.
so it's actually something you have to do
thing
is
down
put that like the plot.
Oh, okay.
Yeah, there's a way to do it.
This is
I figured where I saw it. I mean, I Googled and saw pictures, but I couldn't figure out how to get it.
I did it on PowerPoint.
I know Eric did, but I don't know if Eric did it anymore.
I found this package out there. She said, "Browse it and change that slide." Do volcanoes, like a lot of somewhere
so let's
just.
see like
So that's a little bit.
A lot of the code is already written
Pretty,
on
yeah.
it, so you just put in the cutoffs.
Yep.
I didn't do everything. I tried to try it. Well, I didn't do it.
well
Yeah, I saw one of those packages to make those like really complicated ones with like lots of cutoffs and colors and.
It's just had like 3 colors. I didn't.
There is a package for everything. What's wrong, Keith? I don't know. You should be signed in.
Something like it not being in the path.
like this is my mask.
So see here, it says please complete your changes.
There's like no
Are you learned?
So
So that's
many
because
ways
in
to
these
control
two
just
is
the
your
changes to
numbers. So
I describe
I really just, for mine, I just wrote this in.
Yeah, so this
Now,
is the same.
You just put it in this repository URL,
I did it, there was
and it'll
an
make it.
So I guess it's
like,
different.
it'll make it directly to this list. It's going to put it in. You can specify where you want it. Do you want it?
So do you know where that is?
This PC. Okay.
Good. Okay. So now.
Differences. It tells you the differences between yours, and you can just revert.
Because you want
Because all of them revert. It said stash. Yeah, you can just revert, which is fine.
You can stash those changes if you want. So you just click on commit.
Let me try from
And
just
then-
making it full. Yeah. It's not quite button this.
Click here, just to make sure.
Okay. I think I was trying to go into your rows. It doesn't like that. And so then you should see those files. Right. So yeah, so it's created a new project for you. So anytime you want to get to this, you
Good
just
to
click
go.
on project. So it'll be
So now,
this folder.
skip.
Yep.
See, ta-da.
Code. So that's what it is. And just make sure.
So the Celtic contribute to the wrong rules. And that was that thing. And
Yeah,
now
so-
say cool.
I don't know all the details in that.
So this is gonna update from what we have.
So you just crack all of it.
Huh.
Thank you.
This is the hard part.
Yeah, this is the part that takes a while. Okay, I'm just gonna go ahead and get going because my part is really short and really basic, so I'm happy to go over that with anyone who missed it afterwards because it's pretty short. But I asked you to go ahead and run the chunk where you load your libraries, and then this import chunk here. It's the second one where you pull the data from Prism, and you end up with 3 data sets out of this chunk. You end up with Prism, Prism Long, and Prism Meta. And so I just want to point out one thing. Control. I don't remember how to do it on a Mac. So let's see if I can do it. So if you just go into this import chunk and type in head of Prism, what you'll see is that this data set is 4,600 columns plus. So the problem with that is that it's going to be impossible to plot for us. But when we look at the data, what we have is the same information for every drug individually. So what Matt wrote in this import code, when he changed it to Prism long, you'll notice this pivot longer function, and he's changing, he's creating now a column that is the drug, and these values here underneath each drug are a log fold change. And this is for each different, I think it's a study or round, or I don't know what you want to.
What are we looking at?
This value here is
That's
the
the cell line.
cell line. Sorry, this cell line. So this is the log fold change for each cell line and each drug. But now we're changing it to where, if we look at our head of, oh, come on. If we look at the head function again, but this time for Prism long, what you'll see is we now have 3 columns. We've taken those column names from the Prism data set, and they're now their own column entitled drug. We have X1 is the cell line here. That's the same, but now we have multiple values. So each cell line for each drug and the log fold change for each of those. So this data is just going to be much easier to plot. And we're going to do just a basic plot to start. I'm actually not going to do this Prism meta histogram of the dose.
I'm going to jump in and just
Okay.
interject on
Yep,
one
no
thing
problem.
here. So this is a really key concept here. So this pivoting longer, or making a really wide data frame long. So in the concept of the tidyverse and the concept of tidy data, having tidy data means that there is one observation per row and one variable per column. So wide data, by definition, then is not tidy data. So in this case, our wide data looks like an Excel spreadsheet, something that looks familiar, where we have all of our, if you pull it up again, just head Prism. Yeah, perfect.
I'll do both of them.
Where we've got a cell line, and then drug 1, drug 2, drug 3, drug 4, and then all of the values there. So if we wanted to plot, in this case, the first drug and the log fold changes and the cell lines, we could do that. We could do that within ggplot. We could do that with the code that we know how to do. But when we want to now all of a sudden include a second cell line, we can't, because the second cell line is in a different column. Okay, so what we need to do conceptually is take column 2 and stack it underneath column 1. And it's then going to repeat the same cell lines. So all of the cell lines then are going to be repeated, but the drug now is underneath. Then we do the same with column 3, and we stick it underneath column 1, and so on. And now all of column 1 has our drug information, and all of that stuff that used to be in what we would call cells within Excel, that's now its own column, and the type of data it is a log2 fold change of viability of these cells after treated with a drug. So this is a really important concept, because most of the time we spend getting data tidy so then we can graph it. In this case, there's a single function. It's really intuitive. They've changed the function recently to try to make it even more intuitive, the developers of the tidyverse packages. But without data in this format, we would be limited to plotting only one of these columns, because column 2 through n all has the exact same type of information. Okay, so what we need to do almost every single time we get a data set is tidy it up and make it so that we can plot it. Because now we've got a cell line column, we've got a drug column, and we've got a log2 fold change column. So with these 3 columns, that's 3 different types of information that we can then start to think about plotting. Is that clear? we're going to keep hammering this because until you guys tell me to stop hammering it, because without doing this type of transformation, you can't take advantage of any of the plotting powers within ggplot and within the tidyverse. So you can think about wide, right? This is a wide versus long. So you've only got 3 columns, and how many rows do you have? We can look on the right. So Prism long is 2.7 million observations. So that's really long compared to wide. But really all it did is it took column 2, put it under 1, column 3, put it under 1, and then basically cut and pasted the cell line identities so that when you look at the cell line identities, it's cell line, drug, and what changed.
So is that any different than like transposition and stuff?
It's totally different than transposition. That's a great question. But transposing is going to take all of the x's and make them y's, and all of the y's and make them x's. So if we look at Prism again, to transpose the Prism data set, what we would do is we would take basically all of the cell lines and make them columns, and all of the drugs and make them rows. That doesn't get us any farther because we still only would be restricted to plotting one of these variables. So the mantra is always, it's one observation per row. In this case, an observation is how a cell line behaves in response to a drug.
So Matt, how did it start out again?
So this is how it started.
Yeah, so we import the data, and we've got a very Excel spreadsheet, intuitive, familiar. We've got cell lines by drugs, and each of the values in the middle is a log2 full change.
It had one column of cell line and a bunch of columns of drugs.
Yeah, so
Yeah.
this is it right here. So this is the cell line, this is the first drug, the next drug.
Okay, I got it.
I would open it. Matt's computer's probably faster than mine, but like my computer wouldn't open
You
the.
put all the drugs in one column basically and duplicated the cell line.
Exactly.
Mm-hmm.
Because if you think about this data set, if you try to categorize this, then how a cell responds to a drug and the response to it. So it's a cell line, a drug, and its response. Okay, so it'd be the same as if we had some patient data. We're going to be talking about like metadata that is related to this. So in fact, the advanced version next that Akshay will talk about is going to integrate disparate data types. But we need to get it long in order to plot it, because we need to get it tidy, and that's what ggplot's going to recognize. All right.
You scroll up just
Mm-hmm.
So the code there is Prism, and then, so I slice. If you uncomment that, I oftentimes in
Which one? This one or this one?
Down.
Oh, this one.
There, that
Sorry.
one. So I often write test code. It's a good practice. If you're trying to make sure you want to get it right, you don't want to process a big data set only to have it wrong. So you can go ahead and just run that piece of code. And I don't know why I keep getting those messages.
Mm.
But often that will slice a smaller data set and then try to do that transformation. So that's why slices there is commented out. Whatever, you can recomment it out.
Yeah,
And
if
then-
you look at it though, it made the number of observations smaller. If you want to know what it did.
Yeah, so then, so that's why slice is there. So then pivot longer, you can run the whole thing again. So columns, I want everything to pivot except for the first column, and then names to drug and values to log2 full change. So it's like, what are my names going to be? And that's why my next 2 columns after doing that are drug and log2 full changes, because I told it right there.
Okay.
Okay.
So, when we looked at this Prism long data, once again, we have our cell line, our drug, and our log2 fold change. So, this, I'm just going to go over a little bit of exploratory graphs with you, just looking at the distribution of this log2 fold change information. So it's already in your your markdown file, this ggplot prism long histogram of the log2 fold change. Just go ahead and run that. I'm going to ignore dose for now. It's not a very exciting plot. And what you should see is this sort of histogram here. Okay? But you'll notice that R tells you that stat bin is using bins equals 30 and that you should pick a better value with bin width. So I'm actually going to go ahead and go over this because I only recently really determined the difference between bins and bin width. So what R is talking about here is how it's deciding to group the numbers for the plot, right? So each bar is a range of values between X and Y. And it's saying there are this many count. Notice this is count. There are this many values within this bin, right? So we can change that bin. So if we go in and simply add bin width equals, in this case, I'm going to put 0.1 and then rerun this. What you'll see is now we have much thinner columns. And what I've done exactly here is I've set bin width to 0.1. But what it's done is taken values from 0 to 1 on this plot and divided it up into 10 bins, so a tenth. So that's the 0.1. And so between 0 and -4, there are 40 bins, right? Between 0 and 2, there are 20 bins. And it just gives us, you'll see, we now have like a little bit smoother like distribution here. It kind of gives us a better idea of how the data is spread out. We can do this another way as well. Let's say you don't know how many bins or like what the bin width you want precisely is. You can just say, I want this number of bins total on the graph. So all the way across the values on the X, you can say, I want 50 bins, 50 different bins, and it will automatically calculate the bin width for you. I think it's bins, not bin. Let me check. Yeah, bins. So if we run that, you see we still have thinner bars than our first graph, but now our bars are a little bit thicker than when we set our bin width to 0.1. So this is just, I wanted to point this out because sometimes when you look at these graphs with their default settings, they're not super informative. So when we looked at this without changing the bins, it's not as informative about the distribution of this data. There's, if you like to see a graph with a line instead of the bars, you can try typing in geom_freq_poly, which is a frequency polygon, I believe is what they call it. And we just set the same settings. Note for this graph, you still use bins. So we will still set our bins to 50. If I could type on a Mac. Okay. And you'll see now we're going to get the same sort of plot. It's just going to come out with a line instead of bars. So now this looks a little bit more how we usually think about distribution. So I want to point out something really important here. This is not density, this is distribution and counts. So what you're looking at here is in this bin, this is the number of values that fall in there. That is not the same as density of the data. If you want to look at density, you can type in density for the geom. I know this is, and then get rid of your bins because density works a little bit differently. So now when we do density, you'll notice now our y-axis is density and not counts. So just keep that in mind if you're ever doing these simple like distribution of your data, you want to see what it looks like. Think about whether or not you're using the right ones. And when Akshay shows you how to join the data and go on and do your more complex graph, if you want to see a really good example of why you should use density versus your frequency polygon, I can show you an example where we look at densities based on groups, and it looks a lot different. So that's our simple little plot. I did not go into titles or anything because actually Akshay is going to do that with you. So I'll go ahead and let Akshay come on up.
So the plot I'll be showing you how to make is actually one that Ali came up with, and it's plotting the log fold changes for each of the different phases for a particular mode of action. And I don't know what to call this plot, but it kind of looks like rainfall, so I'm going to call it a rainfall plot. But in order to do that, we first need to join the Prism long and Prism meta datasets. And Matt mentioned that converting the Prism dataset from a wide to a long dataset is necessary to make it a, quote, tidy dataset. But it also is necessary for us to do the join, to combine the two datasets. So in the bootcamp, we spoke about different ways of joining two datasets. And in this case, we'll use a left join. So a left join, if you recall, retains all the rows in your first data frame and all the columns from both data frames. But for a join to work, you need to have at least one variable in common between the two datasets, which we did for the bootcamp example. But in this case, it's a little bit tricky. If you look at, for example, so we'll be joining Prism long with Prism meta. So if you open Prism long, you see these 3 columns. If you open Prism meta, you see there are 11 columns. And it isn't immediately apparent. So there are no common columns right now. So we have to generate common columns using the data we have. So if you look through these data sets, you'll see that Broad ID in the Prism meta data frame looks somewhat similar to drug in the Prism long data frame. There are a few differences. One difference is that in the Prism long data set, it's all lowercase, but in the Prism meta, it's uppercase. Another difference is there are dashes in Prism meta, but in long, there are underscores. And the final difference is in Prism long, you have this extra information here that you don't have in Prism meta. So we need to do a few things to create a new variable in both the data frames that are identical. So to do that, I'm sure there are multiple ways. I mean, there are multiple ways. This is what I came up with. And it's a nice example of using the stringer package to create new variables based on the ones you have. So go ahead and just run all of that, and then we can go through it line by line.
So while it's running, I'll just interject. This is all self-induced because one of the commands that I ran after, one of the functions I ran after importing the data was a nifty little function from the janitor package called clean_names, which then takes a bunch of complicated names and makes them into a clean format by making them all lowercase, by replacing some of the dashes with underscores and so on. So that's a habit that I have just to try to standardize and normalize names and so on. But in this case, if we needed those names to be in a certain format, I suspect Akshay's solution worked, but another solution would be to not run that function after the clean_names. So just a side note that the cleaning and the struggle that Akshay went through to try to get the code to work was all because of me. And so so just to realize or to remember, yes, a lot of the work that you're going to have to do might not be self-induced, and so he'll show you what I'm sure is a very elegant solution to this problem. But the thing to keep in mind is that you have to ask, a question at every single line of code, like, what did this do? Do I need it? Et cetera, et cetera. So just to sort of clue you guys into, this is all self-induced.
But challenges are good.
Yeah.
Ashot, you have a question? No? Oh, I see you're sticky. No. So if we look at the first line, what I've done is I've taken the Prism meta set, which looks like this, and I've piped it into this. So what I could do is I could just change the Broad ID format, this column, but I think it's always dangerous when you start to change the columns that are already there. So I wanted to keep it and use it to make a new column that I'm calling drug meta. So if you remember, to create a new variable using existing variables, you need to use a mutate function. And then I use this function called string2lower, which basically takes all the entries in the Broad ID and makes them lowercase. So that's the first out of the three things we need to get done. The second one is using the same drug meta, I use the string replace all function to take all occurrences of dashes and make them underscores. So when I run those two things, I get this Prism, I save the output as Prism meta new. And if you open that, if you compare that with Prism meta, it's not lowercase. Oh, I'm sorry. You have to scroll all the way to the end to see the new variable you've made, which is called drug meta. And now this is starting to look a lot more like drug in the Prism long dataset. The only difference is this doesn't have that extra information you see in Prism long. So what I next did was I took the Prism long dataset and I made a new variable called drug short, and I used a string sub function to get rid of that extra information. I noticed that if you go from character 1 to 22, so if you sit down and count them, and you cut that out, that'll be identical to what's in this drug meta column in your Prism meta new data frame. So to do that, you use the string sub function, drug, and then it takes 1 to 22, both inclusive and everything in the middle. And then what I did was I left joined using this left joined the output of the first two lines of this code with the Prism meta new data frame, and by the only common variable, which is named drug underscore short in the Prism long set, and drug underscore meta in the Prism underscore meta underscore new. So there's a lot of repetition here, which I apologize for. And yeah.
So
Yeah.
that 1 to 22 is text from 1 to 22 character?
Yeah, so it's basically, so if you go to Prism long, it's from, in this example, it's from B to 6.
Okay.
So even when you run it, it's still working.
So clean names is just a function that basically does a string to lower and string replace, apparently. But the last part, the reason it's not identical is the last part of the unique identifier is the drug dose that they included in that. So that underscore 2 underscore 5 is a 2.5 micromolar drug dose. And then the last is HTS for high throughput screen. And there's some data they have from focus screens. I think we're just using the high throughput screen data.
No, they have two screens, both the screens. Yeah.
Yeah, so in this, what it'll do is, if this is metadata for everything, then they did a high throughput screen and then they did a focus screen after that. So,
But if they were identical, it would have given the same. If we ran clean names on two data sets, and they had identical
names.
it
Yeah.
would have been the same.
Yes, exactly. Yeah. Yeah, because clean names is just a function that looks for something and changes it to something else.
Cool. So if you look at the Prism join data frame now, so in addition to the cell line, drug, and log2 fold change, you have all this extra useful information. And the two variables we'll be using for the plot are MOA, mode of action, and the phase. So great, so we've prepared the data set we need to make our plots. Now, this is, like I said, this is mostly Ali's code, and what the first thing she did was she decided to filter this join data set so that you only get log2 fold changes that are less than -2. And she saved this output in a new data frame called Prism _ big FC, big fold change. So before we go through all of this code for the plot, let's just run all of it. So you hit play. Which will first make the Prism _ big FC data frame, and then should hopefully make a plot that looks like this. And as you can see, you have log2 fold changes on the y-axis, and on the x-axis you have the different phases. And what Ali did was she specifically looked at I should say there are actually two plots here. This is a basic one up here which we can skip, and this is a nicer, a more polished one. So we'll look at the more polished one. And what Ali, the subset of drugs she looked at, all had the MOA tubulin polymerization inhibitor, and she used a string match for that. Now, to show you how this plot is built line by line, I'm going to try to make use of this thing called a flipbook, which is this approach. This is a package developed by Gina Reynolds, and it's a way of teaching people how to use dplyr and ggplot. So this is the same code as the one you have, so starting from line 78. It's just that this is it's in a long format, and the reason for that is it's so that it highlights what each function does line by line. So we'll see that. So the first line is just your data set. So here you'll see the code develop, and on the right hand side you'll see the output change as you add more and more lines of code. So the first line of code is just your data set, which is Prism _ big FC. So what you see is a data frame. When you pipe it into ggplot, you just see a blank canvas, because ggplot needs more than just your data set. It needs you to specify axes and what kind of plot you want. So the first thing we do is specify the x-axis by putting in x equals phase in the aesthetic function. And so you can see now there's an x-axis. The next thing is to specify the y-axis, which is log2 fold change. Now the reason you don't see anything on your plot is you haven't specified what kind of plot this is. So, yeah.
Just a note. You were to run ggplot x equals y equals, you're not going to get that. This is just like a really nice way to show you how ggplot builds the plots.
Yeah, you would never.
If you run just a ggplot function, even with aesthetic values, you will get nothing.
Yeah. And also, you would never actually code like this. I mean, you could, but probably wouldn't. This is just for the purpose of showing you what each line does, or each element does. So we then add the geom jitter, which is like geom point, except like in this case, for example, if you had 100 data points that all had a log2 fold change of -4, you would just see 1 point because they'd all be overlaid if you use geom _ point. But if you do geom jitter, it applies a randomized mild jitter, so you can see more than just 1 point. And within that, what Ali did was she specified the color aesthetic to be equal to, and again, she used a function from the stringer package called string match. So what that function does here is it takes the variable MOA, mode of action, and only picks those that match this tubulin polymerization inhibitor. And then what she did was she applied an alpha equals 0.1. If you remember, alpha is what you use to adjust the transparency. So you get this. This is the basic plot, and all the ones that are the dots that are pink match this tubulin polymerization inhibitor MOA, and everything that's gray is everything else. Now, this can be made more pretty. So one way is to use the scale color manual function to specify to convert all the pink dots here into this nice shade of dark red, and everything else has no color. So this is nice. Now the data points of interest pop, but you also have this legend here, which is unnecessary.
Point out one thing before you move on. I made multiple versions of this, and in the version that I said, actually I used dark red, but you can also use the hex codes and just Google R color codes, and it will show you the shades and the codes that you can use for them, and you enter them the same way you do here. You just enter the actual hex number.
Hex numbers offer you more flexibility, but you have to, unless you have an amazing memory, you will have to look them
They
up.
also give you like more specific shades. This was like close enough.
So now, I want to get rid of this unhelpful legend. So one way to do that is to use the guides function. And since the legend corresponds to the color aesthetic, you do color equals none in quotation marks. And then one trick to get this, to change this from a base ggplot look to something a little more polished, is to use one of the various theme functions. So they're theme _*. So there's theme _minimal, theme _black, and so on. So I use this theme _BW, which I like because it's a white background with a nice outline that acts as a frame. So everything is looking a little bit nicer. But what this plot needs now is a title. This x-axis label is phase with a lowercase p. I want an uppercase p, and a few other things. So then for that, you can use the labs function. And then within it, I specify x equals, and I type out phase with a capital P. I give it a title, call it rainfall plot. I give it a subtitle. And caption is down here, so you can put your name by whatever your name is. And that's how the plot that you see here is built. And that's it. Any questions?
So I just wanted to point out here, like if you don't remember this data set and you're like me and you don't retain information quite as strongly, the whole log2full change is looking at how will these cell lines grow in these drugs. So the negative log2full change means they're not growing or proliferating as well. So I did this plot with tubulin polymerization inhibitors because I expect those to have larger log2full changes. But if you change your mode of action to something like calcium channel blocker, you might be more surprised. Like, sure, you don't expect as many to maybe inhibit growth the same way, but you might be surprised that some of them really do.
Yeah, and then you could, an easy way to look at that is to just copy paste this and just change the term to correspond to the MOA you want to look at. Or you can make a Shiny app and then just click what you want. And this is like 90% of the way to being a Shiny app.
We'll save that for next week,
Yeah.
next month. All right. Any questions? No? All right. One last activity then. So if you come back to the project and you open up normal tissue HPA. So this is a website. So one of the things we also want to do with this meetup is to talk about resources for data. So one website that has a lot of publicly available data is called the Human Protein Atlas. And they continue to increase the types of data they have here. But go ahead, shout it out. What's your favorite gene? Not all at once. What's that? What, OS2? NOS2. All right. So here, nitric oxide synthase. You should have said that. All right. So what you can do here is you can see the summary, and then they've got different atlases. This is the human protein atlas. So here, it looks like we've got different distributions of the NOS2. We can then rank this by expression, and it looks like this is nasopharynx, colon, rectum, appendix, some brain regions, etc. And this is the protein overexpression. This is RNA, another data set, etc. So you can go through this. We can also come to the top, and we can look at in the cell, where do we find it? And if we go to expression again, this is a cell line category. So these are cells that have high levels of NOS2 and so on. Then we can go to, it looks like we don't have much subcellular localization information. Here's pathology, scored across several cancer tissues and so on, brain and blood. We can also download some of these data. So if we go here, we come over to downloadable data, you can find either programmatic access, search results, single entry, archive data, or you can simply download the tissue data sets. And I've explored a couple of these. One that we're going to work with today, and this is going to be the homework for next month, is going to be looking at the normalized tissue expression, which is the where did you go? Let's see. The file is called RNA tissue consensus. All right, so then number 4. So what we're going to do is we're going to download the data from number 4 here. This looks like consensus transcript expression levels summarized per gene in 74 tissues based on transcriptomic data from 3 sources, HPA, GTEx, and Phantom5. So this is interesting because depending on which data set, which data source you query, you'll get different values. So NOS2 might be present in one tissue at a high level in one data set and not in another. And so this is an interesting attempt to try to normalize it. So you've got 2 approaches here. One is we can click on this, we can download the file, we can drag that file into a data directory and then read that in R. And that works, except that if I do that and I want to share the code with you, you guys don't have the file. So you could download the file and repeat the instructions, and that's exactly what I tried to do for you here. So I cut and paste some information here. So we have HPA, this is Human Protein Atlas, Normalized Tissue Expression Notebook. So this is the information about the data set, and you can either, spell correctly or not, download the file and place it in the data folder, or you can run the code below. So today I looked up how to save the URL as an object, but then what we can do is if you just try to import this URL points to a zipped file, and that zipped file is a bunch of gibberish. So what we need to do is we need to temporarily store the information from that zipped file as a binary object that R can recognize, and that's what this code does. So we've got a temporary file here, and then what we do is we download the file from the URL, we stuff it into this temporary file, and the mode here is binary, and that allows R to download that zipped file, store it temporarily, and then import it. And so then we call something normalized tissue. We read TSV. Recall that TSV is tab separated value. And then we clean names. So this all looks familiar. The new thing here is that we've got one extra step. You don't need to worry about this so much. We can go like this just to clear, just to show you. Okay. And then we can run these lines. And we'll wait a moment. And what we should be able to do is download this file as downloading, and then it will take a second or two to unzip. And then what we have is parse column with gene, gene name, and tissue. And lastly, the normalized expression value. So then if we run this line here, we can see that we have the data in a format where we have gene, gene name, tissue, and NX. NX, recall, is normalized expression. So we can do some things like count. So how many within this data set, we're counting the normalized expression value, and we sort is true. So here we've got a lot of tissues with a normalized, or a lot of tissue gene pairs with a normalized expression value of 0, as we'd expect. And then we can go on up to some very high normalized expression values. We can then say, well, let's just look at all of the data, and this is a log 10 transform normalized expression, and we can see that we've got a bunch at 0, and then again, recall that this is log transformed, and we can see that we have, if we take out the log 10, just to show you what the raw data look like, and run that line. You guys can do this. Go ahead and run this code, import it. We could see something like this. Okay, that's not really informative. This is a histogram binning, like Ali talked about earlier today, the different values. And you can say, well, maybe not surprising, the most abundant value here is 0, which is why I did the log 10 transformation. Put that back, run it again, and that then helps us see the data in a little bit better distribution. Okay? So go ahead and do this all now. Go ahead and just run this first chunk. You should get the log 10 normalized view just like this. All right, now, the next thing I wanted to do is go ahead and filter on your favorite gene. So here we said NOS2 is one favorite gene. So we take normalized tissue and then filter gene name equals NOS2. And we could do that, and we get all of the data for NOS2. And this is now going to be alphabetical based on tissue. Not so helpful. So we added one extra line here, arrange by descending order the normalized expression for the data that we look at, and then we can see NOS2 is high in the small intestine, appendix, duodenum, and so on. So Matt, does that make sense? Is NOS2 a primarily gut sort of gene?
I mean, it's induced by cytokines, so the gut will.
All right. So bacteria live in the gut, and bacteria make cytokines. So there you go. Super simple. No, so we can look at this, and we can either say this makes perfect sense or it makes no sense at all. But we can do the same thing, and let's actually remove a couple of these commands. So flipbook would have been useful here. So we can go like this, and we can get the exact same data. All right. And then we can arrange it. That looks like what happened? Object NX not found.
NX is hashtag out.
Okay, just go like this. So what I wanted to do here was to filter. I was going to show you why in just a moment. Okay, so what we can then do is we can take the output of this, which is this table here, and we pipe it straight into a ggplot. And one of the things I wanted to do is really just, I'll do this slowly with you guys here. So if we take this, we're going to work together. You guys can do this. You can follow along. So we take this code, this chunk right here, and we run that, and this is what we see. And then we ggplot, and then we geom column AES x equals, let's see, we want tissue, y equals nx. That should give us a beautiful looking, completely illegible plot of NOS2 with our tissue. All right, now, I knew that was going to happen because we got a lot of different tissues here, so let's add a chord flip. Oh, flip. I flip it around. Okay, we're getting a little better. But there's two things that I want to do here. So one is I want to get rid of some of the ones that's 0, okay? Because I'm not really interested in that. So I can add a filter as this, and nx is greater than 2. So that gets rid of some of, 2 is a little bit arbitrary. Let's say, 1.5. Okay, that looks a little nicer. But now this is in alphabetical order, starting at the bottom. So there's a nice little command that's called FCT reorder. FCT stands for factor. And what we can then do is we can factor reorder. And what do we want to reorder? We want to reorder our tissues. So that's what we add here, an FCT reorder. And we're going to reorder our tissue. And what are we going to reorder it by? By the normalized expression level. And that then looks like this. Okay. And then we can lastly clean it up a little bit. We can do like a theme, like minimal, there's one package by Klaus Wilke that makes a cow plot package, and cow plot is a very sort of clean looking theme cow plot. Can't find it. Let's go like this. Make sure that this is loaded. So what I did is I just loaded this package. Okay, and we go like that. And then we get our, let's see, we need to change the title here. So this is NOS2. So this is our tissue distribution of NOS2 expression. Now, what you should be able to do is if you take this is code that you guys have, if you have this file open, this normal tissue HPA file open, go ahead and change NOS2 to your favorite gene and go ahead and change the title here. And then go ahead and play around with this threshold cutoff to see, what looks like, good data, something interesting. 1.5 we said might be a little bit more interesting. And we have no color here. We have color as a variable, so we could color it. So I'd say at minimum what you can do is between now and next month is go ahead and just do those couple of cut and paste that I showed you. But we could do things that are a little bit more interesting. Perhaps you're not interested in a gene. Right? I said, tell me your favorite gene, and Darren shot me a look, and he says, I don't have a favorite gene. I have a favorite tissue. Right? So we could do the same thing. We could say, instead of gene name equals NOS2, we could say tissue equals what? We like the amygdala. Right? And we could still do this. And then is this going to... tissue distribution of MIG, MY, GDALA. But then here what we're going to do is instead of tissue, we're going to go gene. And then let's actually, instead of filtering, there's a function that's called top n. And then we can take the top 10. Something like that. Is that going to work? Yeah, there's a lot of unknown genes that are really highly expressed in the amygdala. Awesome. Okay, so opportunity for discovery. Nope. Yeah, actually, we should do that. So if I go like this, what do I want? I want gene name, not gene. Thank you. There we go. These are the genes that are highest in the amygdala. Woohoo! Publish it. All right. No, but go ahead. So it's 5 after 5. We'll stop here. But this is your homework for next month, is to go ahead to take these data to either look for your favorite gene or your favorite tissue and look at the genes. And so what we'll do next month is we'll have a short, again, beginner intro vignette for the for this data set. We'll also do a more complicated analysis for this data set. And maybe if you guys are feeling brave, you can share your favorite gene or your favorite tissue. So with that, we'll wrap up.